Okay, so let's get started. Good morning, everyone. Welcome back to week 2. Hope you had a good first week back at uni. I see only, a quarter or a third of you have survived so far. I wonder why. So this week we're going to talk about sorting algorithms. And before we get started, I wanted to address some feedback which we got last week. First thing was the webcam. So I finally got it working, so you should be able to see me on the live stream and on the recording. The other thing was, ads on YouTube videos. So unfortunately, YouTube doesn't let us remove ads from our videos unless we are part of the YouTube Partner Program, and our account isn't. So I think the minimum requirement for you to be able to join the partner program is to have 1,000 subs, which we don't. So, if you want to remove ads from videos, then sub to the channel. But also there are other ways of removing ads, which I don't need to mention. So, yeah. Okay, so now we are going to head over and look at sorting algorithms. And we're covering sorting algorithms now because it gives us a good chance to practice our time complexity analysis. So we'll go over a bunch of sorting algorithms today and then a few more on Thursday. Okay. So first of all, why do we care about sorting? Right. As we saw last week, if we have a sorted array, right, we can use an algorithm called binary search, which lets us search for things really efficiently. Right, lets us search for things in O of log n time, which is much better than the alternative, which is when the array isn't sorted, which is linear search, right, which has a worst case of O(n) time. All right, and obviously sorting lets us arrange data in useful ways. So for example, if you have a list of students and it's sorted, then it's much easier to find a student. And sorting also provides a useful intermediate for other algorithms. So for example, if you want to know how many duplicates there are in an array, if the array is already sorted, then that's really easy to figure out, right? Because all the duplicates are going to be next to each other. Okay, and also if you want to merge two collections, sorting makes that much easier, right? Because both the sequences are sorted, and that means you can start from the beginning of each collection and iterate through them. Okay, so what is sorting? So obviously sorting is just a process which involves arranging a collection of items in order, right? And in these 2 lectures, we're going to be focusing on arrays, right? But of course, you could also consider sorting linked lists. You could also consider sorting files and so on. And when we sort items, we usually sort them based on some property, right? Because in the real world, you're not really going to be sorting just raw integers, right? Usually you'll be sorting things like structs or records, things that have lots of properties, right? Or fields or attributes, right? So suppose we have a student struct, right? And the student struct contains an ID, contains a name. We might be interested in sorting the students by one of these things, right? So we might want to sort by ZID. We might want to sort them by name. So the thing that we're sorting the items on is called the key, right? So if we're sorting by ZID, then the key is the ZID, and so on. Right? And obviously, if you're trying to sort things, then you need a way to compare them, right? So if you're sorting by numbers, then numbers are sorted numerically, smaller numbers. If the number is smaller, that means the item is considered to be smaller. And if you're sorting strings, then the strings are sorted alphabetically, okay? Usually. Okay, so So I already said we're sorting arrays of items, and the items could be as simple as things like integers, characters, doubles, or they could be strings, or they could be structs containing multiple different fields. Right, and the items are sorted based on a key. All right, so here's an example of sorting. So here is our regular student struct. Right, each struct contains an ID and a name. Right, now if we sort by ID, then the result is that the final array should be sorted by ZID, right, in ascending order. Right, so the array contains the same items before sorting, but now they're sorted by ID. And if we sort by name, then the students will be sorted by name, right? And notice that, sometimes the keys are unique, right? In this case, we know that every student has a different ID. So if we sort by ID, then, right, there's not going to be any, variation as to what kind of output we're going to get, right? But if we sort by name, right, multiple people might have the same name. So here, for example, we have 2 students with the name John, right? So how these students are going to be ordered after we sort by name kind of depends on the sorting algorithm. And it depends on something called stability, which we'll talk about in a bit. Okay, so this is how we're going to view the sorting problem throughout these 2 lectures. Right, we're going to suppose that we have an array of items, and we're going to sort the array between 2 indices, right, between index low and index high. Right, and often you'll want to sort the entire array, which means low is going to be 0 and high is going to be n-1. But having this function where you sort between 2 indices is useful because later on we're going to look at recursive sorting algorithms, and in this case it's useful to be able to specify which part of the array you want to sort. Right? Maybe I want to sort just the first half, then I'm going to sort the second half. Okay, and here are some examples of sorting algorithms. Right? So there are a couple of elementary sorting algorithms which are pretty much basic sorting algorithms like selection sort, bubble sort, insertion sort, shell sort. There are some interesting algorithms called divide and conquer sorting algorithms, which we'll discuss what divide and conquer means later. So these are merge sort and quick sort. And there are other sorting algorithms which are kind of special, called non-comparison based sorting algorithms like radic sort. Right, so we'll look at most of these over the next 2 lectures. Okay, and we're looking at sorting algorithms because it gives us a nice chance to analyze algorithms. So when we're analyzing sorting algorithms, there are 3 kind of cases we want to consider. Right, there is the random order, so give the sorting algorithm a random array and see how long it takes to run. There's also sorted order, so what happens if you give the sorting algorithm something which is already sorted, and reverse sorted order, so what happens if the array is reverse sorted. Right, so we're interested in sorted order and reverse sorted order because these are kind of the extremes, right? In the case of sorting, right? Sorted array is the most sorted something can be, and a reverse sorted array is kind of the most unsorted something can be, right? It's like the opposite of being sorted. And random order is useful because it lets us kind of analyze the average time complexity. Right. Okay, and when we analyze the time complexity, we're going to use n, which is the number of items in the part of the array that we want to sort, so high minus low plus 1. We're going to have c, which is the number of comparisons between items, because when we're sorting, we often need to compare 2 items, compare pairs of items to figure out how they should be ordered, and also s. So in sorting algorithms, we often swap elements. So we use s to count how many times we swap items. Okay, so that's how we're going to analyze things. In addition to time complexity, there are a couple more properties that we're interested in for sorting algorithms. Right, so the first one is stability. Right, so what is stability? So a stable sort is a sort that preserves the relative order of items with equal keys. Right, so as an example, before when we looked at this student example, right, if we have two items with the same key, so for example, we're sorting by name here, and we have multiple people with the same name, right, if the sorting algorithm is stable, then the people with the same name, for example, the Johns, are going to remain in the same relative order after sorting. Right, so in this case here, where we have our input array of students and then our outputs after we sort by name, we see that the Johns are in the same order, right, after sorting, which means that the sort was stable. Okay, so you have stability. A stable sort preserves the relative order of items with equal keys. Right, and a stable sorting algorithm. Now, I want to draw a distinction between stable sort and a stable sorting algorithm. Right, so a stable sorting algorithm always performs a stable sort, right, regardless of the input that you're given. Right, now, an unstable sort can sometimes reduce a stable sort, right, depending on the input, but it's not guaranteed to produce a stable sort. Right, so here are some more examples. Right, so here I have a bunch of cards where each card has a value and a suit. Right, now notice that we have a couple of different cards with the same value. Right, so we have 2 6s and 2 4s. Now if I do a stable sort on value, right, the 4s remain in the same order after sorting, and so do the 6s. Right, so originally we have 4 of diamonds, then 4 of spades. After sorting, we have 4 of diamonds and 4 of spades, and 6 of clubs and 6 of hearts, 6 of clubs and 6 of hearts. Okay, so this is an example of a stable sort. Now here is an example of an unstable sort. Right, so before sorting, we have 6 of clubs before the 6 of hearts, right? But after we sort, the 6 of hearts occurs first, and then the 6 of clubs, right? So the sort has changed the order of items with equal keys, which means that the sort was unstable. Okay, and even though the 4s remain in the same relative order, the 6s don't, which means it was unstable. Okay, so why do we care about stability? So when we sort the same array multiple times on different keys, often we'll want the items to remain in the same relative order. Right, and some algorithms rely on this, such as radix sort, but that's on Thursday. But here's an example of why we might want a stable sort. Right, suppose we have an array of first names and last names. Right, so a bunch of people. And what we want to do is to sort these students by their first name. And if multiple students have the same first name, then we want them to be sorted by last name. Right, then one way we can do that is to first sort the array by last name, so sort them by their last name, and then sort them by their first name using a stable sort. Right, so if we sort by the last name first, then the students are going to be sorted by last name. Right, so we have B, Bennett first, then H, Hatter, then Renzella, Shefford, and Taylor, and so on. Right, now if we sort by first name, then the students are going to be ordered by their first name. Right, so we're going to have Alice's first, then we're going to have Andrew's, then Jake, then John. But since the second sort is stable, if two people have the same first name, right, well, when we did the first sort, right, the students were sorted by last name, right, which means that if we then sort by first name, if two people have the same first name, then the last names should remain in the same relative order, right? So after we sort by last name, right, Andrew Bennett, for example, occurred before Andrew Taylor, right, even though they're not next to each other. But after we sort by first name, they're going to remain in the same relative order. So since they have the same first name, Andrew Bennett's going to appear before Andrew Taylor. Right, if we don't use a stable sort, then these two people could end up being swapped, right, after we sort by first name. Okay, so one example of where we might care about having a stable sort. Right, where don't we care about having a stable sort? Well, if all the items have unique keys, then there aren't going to be any pairs of items with the same key, so stability doesn't matter. If the key is the entire item, then stability also doesn't matter. For an example of that is sorting an array of integers, right? If you sort an array of integers, then the integer is the entire key, and it doesn't matter if the algorithm is stable or not, because you won't be able to tell between two integers which are the same, right? You can't tell if they've been swapped or not, so it doesn't matter. Okay, the other property that we care about is adaptability. Right, so how do we define adaptability? An adaptive sorting algorithm takes advantage of existing order in its input. Right, so that means there's something about the algorithm that allows it to sort sorted inputs or nearly sorted inputs much faster than random inputs or reverse sorted inputs. Right, so it's something about the nature of the algorithm. And here's where there are kind of different definitions of what an adaptive sorting algorithm is online. So I want you to use this definition, right? So when we ask you what is adaptability, make sure you follow the definition that we give you. An adaptive sorting algorithm takes advantage of existing order in its inputs. And here's where you need to be careful, because we said that an adaptive sorting algorithm will sort a sorted input or nearly sorted input much faster than a random input. But just because a sorting algorithm sorts sorted input faster than random input doesn't necessarily mean that it's adaptive. All right, so I have an example here of a sorting algorithm which isn't adaptive, right? And on the x-axis is the input size, on the y-axis is the number of seconds that the algorithm takes. And we have data for random input and sorted input, right? So you can see that the algorithm does sort sorted input faster, right, than random input. But the question is how much faster, right? It turns out that this is just like a constant multiple, right? So the algorithm manages to sort sorted input faster than random input by a constant factor. And this isn't really what we consider to be adaptive. Right, here is what we consider to be adaptive. Right, so here's an example of an adaptive sorting algorithm, and you can see that the growth rate of the time it takes to sort random input is much bigger, right, than how long it takes to sort sorted input, right? And in fact, it looks like it takes a constant amount of time to sort sorted input, but it doesn't. This is because it's just so fast that it just looks like a straight line, right? So if you use bigger input sizes, then it'll look like a straight line going up linear. All right, so this is kind of what we would get if we use an adaptive sorting algorithm. Okay, another property that we care about is in place. Right? So an in-place sorting algorithm is one that sorts the data within the original array, and it doesn't use any temporary arrays. Okay, and you might care about whether your algorithm is in place or not, because maybe you're constrained in how much memory you have. Yeah.
Out of curiosity, when
Yeah.
Does that mean this isn't just for arrays? Like this could be also for linked lists?
Yeah. So yeah,
That makes it.
this could also apply to arrays. Yeah, to linked lists as well. Yeah. So pretty much it's whether you need to create a temporary array to store a bunch of items or not. Creating just one variable to store one item temporarily is fine. But if you need like a big array to store things temporarily, then it's not in place. Okay, now here is what we will see in the code in our sorting algorithms. So we're going to have a function which takes in an array of items. Right now, you might be wondering what is this item type? We'll see in a bit. And we'll also take in low and high. Remember, this is the we use these to indicate which part of the array we want to sort. Right? Low is the index of the leftmost item, high is the index of the rightmost item. Okay, and we'll also often need to swap things. So we're going to have a helper function to swap elements at 2 indexes. Right? So this function here will swap elements at indices I and j. Okay, so what is this item type? So the item is going to be a type def. Right? If you haven't seen type def before, it's a way to give a new name to a type. Right? So, for example, if we want to sort integers, then at the top of the code, we would have something like this, type def int item. And that means instead of writing int in our program, we can instead write item. Right? And another example is if we want to sort strings, then we would have something like this, type def char star item, right? Because remember, char star is a pointer to a character, could be a pointer to an array of characters, which is a string. And this means that instead of writing char star, we can write item instead, right? And the benefit of this is that we can change what type we want to sort without actually changing the sorting algorithm code. Okay? Because in the sorting algorithm code, we can just write item, and if we change the type, then we don't need to do anything about that. Okay? And in addition to type defs, we're also going to use a few macros, which are hash defines, which look like functions. Right? And we use these to determine how to compare items, right? And also how to extract keys from an item. Right? So, for example, if we sort integers, then we're going to have this type def int item. Right? Remember, that means instead of typing int, I can say item. And we compare integers. In our sorting algorithm, we might want to figure out if an item is less than another item, whether an item is less than or equal to another item, whether an item is greater than or equal to, and whether an item is greater than. Right, so we have these 4 macros, which let us define how the items are compared. Right, so when we're sorting integers, then we just use these operators, right? Less than or equal to, greater than or equal to, and greater. But if we want to sort more exotic item like struct, then we might want to define how to compare things in a different way, right? So if we have a bunch of structs, each containing a name and a course, and we want to sort the items by name, right? Then since the names are strings, we want to use strcomp, right? Instead of just the less than and greater than operators. Okay. So yeah, that is the introduction to sorting. So now we're going to head over and look at some basic sorting algorithms. Okay, so the first few sorting algorithms that we want to talk about are the basic sorting algorithms. So these are selection sort, bubble sort, insertion sort, and shell sort. And they all have something in common. So selection sort, bubble sort, and insertion sort are what we call ON squared algorithms. So these algorithms are ON squared in the worst case. Now selection sort, shell sort is going to be a bit faster than ON squared, but it's still going to be ON to the power of something, right, where that something is greater than 1. Okay, so first sorting algorithm is selection sort, right? And how does selection sort work? So here's how. So it's pretty much the most basic sorting algorithm you can think of, right? So the method is, first of all, you find the smallest elements in the array, right? After you found the smallest element, you swap it with the first item, right? And that guarantees that the smallest item is now in the right place, right? In the second iteration, you find the second smallest element in the array, and then you swap it with the second element, and that guarantees that that element is in the right place now. Then you find the third smallest element, swap it with the third item, and so on, right? Until you've gone through the entire array, and everything is in its correct place, right? And each iteration is going to improve the sortedness of the array by 1 element, okay? So here is an example of selection sort. So suppose we want to sort this array, right? In the first iteration, we're going to find the smallest element, which is 1, and then swap it with the first item, which is 4, right? So we're going to swap these two, and this is the result. Right, then we're going to find the second smallest element, which is 2, swap it with the second element, which is 4. So now this is what we get. Then we find the third smallest element, swap it with the third item, which is 7. And this is what we get, and so on. Right? So I don't think I need to narrate all of this. So we'll swap the 4 with the 7. The next smallest element is 5, so we'll swap that with the 8. Then here, the smallest element is actually the first element in this unsorted part of the array, so we don't need to do anything. Then we swap the 7 with the 8, and then we're done. Okay, so there is selection sort. Now, we can also go through a visualization of a bigger array just to demonstrate. So here's a really nice website called VisualAlgo. It's really good for visualizing a bunch of different algorithms. So we're going to take this slightly bigger array and run it, and run selection sort on it, and you can now see the actual animations happening, right? So that's nice, right? Every iteration we find the smallest element out of the unsorted part of the array, and we swap it with the elements, with the first element of that part of the array. Okay, so that is how selection sort works. Okay, so here's the implementation of selection sort. Right, so remember, we want to sort this array of items between index low and high. So we have 2 nested loops. Right, the outer loop is going to be iterating through each index of the array, starting from low, going up to high. Right. During each iteration, we find the index of the minimum item, right, starting from index I. Right, so in this inner loop here, we're looking for the item with this, the smallest item. Right, so initially we initialize the min index to I, and then we iterate through the rest of the elements, and if that element is smaller than the one that we currently have, so if items j is less than, that's what LT stands for, less than items bin, then we set min to j, and we keep going. And once we've reached the end of the array, we've found the smallest item, so we swap index min with index I, okay? So that is how selection sort works. Okay, so now we want to talk about the time complexity of selection sort, right? In the best case, the worst case, the average case. So we said before that when we analyze sorting algorithms, we usually consider the number of comparisons and number of swaps. Right? So last week we talked about analyzing algorithms by counting the number of line executions, going line by line, counting how many times each line is executed. For sorting algorithms, usually it's sufficient to just count the number of comparisons and swaps, because these operations tend to be at the most deeply nested level of the algorithm. Right? They tend to be on the inside in the deepest for loop. Right? So we usually consider these. So let's look at how many comparisons and swaps selection sort performs. So in the first iteration, where we're looking for the smallest elements in the array, so that's going to take n-1 comparisons, right? Because we take the first item, and then we compare it with the rest of the items, right? So, and if we find a smaller item, then we take that as our minimum item, and then we compare it with the rest, right? So that's n-1 comparisons. And at the end of the iteration, we perform one swap. Okay. In the second iteration, right, now we have n-1 elements remaining because we've already put the smallest item in the right place. Right. So to find the smallest item out of the remaining n-1 items, that's going to take n-2 comparisons, and then at the end of the iteration, we perform one swap. And this continues until the final iteration, where we have one iteration and one swap. Okay, so the number of comparisons looks like an arithmetic sequence, right? It's going to be 1 plus 2 plus 3 plus blah, 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 all the way up to n-1, right? So that's going to equal to this thing over here, half of n times n-1, right? And that's on squared, okay? And the number of swaps is going to be n-1, but that gets dominated by the number of comparisons. Okay, so the cost of selection sort is big O of n squared, and this is the same regardless of how the array is sorted at the start, right? Because even if the array is sorted, we still do the same thing, right? We go through the array and find the smallest element. The element just happens to be at the start. Then we go through and find the second smallest element. That happens to be at the start, and so on. Okay, so that kind of clues you in as to whether the algorithm is adaptive or not. All right, but now let's talk about the properties of selection sort. So for those of you who aren't looking at the slides and are getting spoiled, let's think about stability first. Right? So is selection sort stable? Put your hand up if you think selection sort is stable. Only a few people. Okay. Well, selection sort is unstable. And well, you might think it's stable because when you're finding the smallest elements, right, if that element occurs multiple times, then you're selecting the first one, right, and swapping it to the beginning. But it turns out that selection sort is unstable because when you perform the swap, right, the other item that's getting swapped might move over another item with the same key. Right, so here's an example of that. So, for example, suppose we have this set of cards, right, and we want to sort the cards by value, right? Now, the smallest item in this array of cards is the 2, right? So if we swap the 2 with the smallest item, which is, with the first item, sorry, which is this 6 of clubs, right, the 6s are going to end up in the wrong order, right, after sorting. So, yeah, selection sort is unstable. Here is a, okay. Yeah, we already saw that selection sort was not adaptive. Okay, so here's a summary of the properties. Right, so it's unstable because of long-range swaps. It's non-adaptive because the sort performs the same steps, regardless of whether the array is sorted or not. and it's also in place. Okay, so that's selection sort. Oh, yeah, we have some questions.
Can we make it stable by making it rather than just less than equal? So we'll get overridden by the last limit?
So so the question was, can we make it stable by changing the less than to less than or equal to? So the problem with that is what happens now if we have two items with the same smallest key, right? Because if that happens, then we're going to take the last of those items and swap it, and now those are going to be in the wrong order. Yeah, so think about like 2, 1, 1. Yeah, the 1 is going to be swapped, the last one is going to be swapped to 2, and now the 1's are in the wrong order. Yeah. Question?
Can you explain how you got the C and S on the next slide?
Yeah.
Explain how you got the C and went from the C equal to that
Yeah.
to S here.
Yep. So the question was, explain how we get this C equals this expression. So it comes from adding up all the comparisons during each iteration. So during the first iteration, right, we're looking for the smallest elements, right? And that's going to take n-1 comparisons because we start with the first item, then we compare that with the rest, right? During the second iteration, right, the first item, the smallest item is in the right place. So now we need to find the smallest item within the remaining n-1 elements, right? So that's going to take n-2 comparisons, right? In the next iteration, finding the smallest element is going to take n-3 comparisons, and so on. So what we get is this arithmetic sequence, right? n-1 plus n-2 plus blah, 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 plus 1. And that happens to equal to this expression here. Yeah?
And you got rid of the constant to get S.
Sorry?
How did you get from C to S?
S is the number of swaps made. So in selection sort, we make one swap at the end of each iteration. So there are n-1 iterations, so that's n-1. Yeah.
So to get the time complexity, is it just taking the maximum between C and S, or is there extra analysis that you have to do?
Cool. So question was, when analyzing time complexity, do you just take the maximum of C and S? Or is there more analysis you have to do? In the case of these basic sorts, like selection sort, bubble sort, and insertion sort, that's enough to just consider C and S. Because these operations tend to be they tend to be like the operations that are performed the most during this sorting algorithm. So in this case, it's the comparison that gets performed inside the nested for loop. So this means that, whenever this loop runs, this comparison is going to be performed. And the swap isn't performed as many times, but that's fine because the comparison will end up being greater than the number of swaps. Yeah?
And how about space complexity?
Space complexity. So with space complexity, usually we consider how much extra space the algorithm uses, not the amount of space that's given. So in selection sort, we only end up using how many variables? A constant number of variables. Like, right, we have int I, int min, and int j, and that's all the variables we need, right? Regardless of how big the array is. So because of that, the sorting algorithm takes O1 space, constant amount of space. Okay, so cool. So that's selection sort. Now let's talk about bubble sort, right? So how bubble sort works is it makes multiple passes from left to right. So starting from index low to right. And on each pass, we're going to compare adjacent elements, and if any pair of adjacent elements is out of order, then we swap them, right? So, for example, if we are going through an array, and at some point we see a 5 on the left and a 3 on the right, then we swap them, right? And we do this all the way from low to high. And the reason this is called bubble sort is that the larger elements will end up bubbling up to the top, right, or to the right side of the array. Okay. And also during a particular pass, if there are no swaps made, then that means the array must be sorted, right? Because, if there are no swaps, then that means there aren't any pairs which are out of order. Okay, so here is an example of bubble sort. So suppose we want to sort this array. Right now, during the first pass, we're going to start from the left-hand side of the array, and we're going to compare adjacent pairs of elements. Right, so first, we're going to compare 4 and 3. Right now, since these are out of order, we're going to swap them. Right, so we swap them now. Now we compare the 4 and 6. Right now, these aren't out of order, so we don't swap them. Then we compare 6 and 1. Right now, these two are out of order, so we swap them. Right. Now we compare 6 and 2. These are out of order, so we swap them. And then we compare 6 and 5. These are out of order, so we swap them. Right. And the final result of the first pass is that the largest item is guaranteed to be at the end of the array. Right. That's because the largest item is always going to be swapped with whatever's on the right of it. Okay, so that's the first pass. Now, in the second pass, let's see what happens. So we're going to start from low again, right, from the left-hand side of the array. We're going to compare 3 and 4. Right, those are not out of order, so we don't swap them. Then we compare 4 and 1. These are out of order, so we do swap them. Then we compare 4 and 2. Right, these are out of order, so we swap them. Then we compare 4 and 5. Right, these are not out of order, so we don't swap them. And the result of the second pass, and we stop here, right, because we already know that the largest item is already in the right place. So we stop just before we reach the end of the array. Right, so here is the result of the second pass. Right, the result is that the second largest element is guaranteed to be in the right spot. Okay, now let's do another pass. So third pass, we compare 3 and 1. Those are out of order, so we swap them. We compare 3 and 2. Those are out of order, so we swap them. Then we compare 3 and 4, and we don't swap them. Right, and the result now is that the third largest item is guaranteed to be at the end in the right place. Right, and the process continues until either we've performed n-1 passes, or until there is a pass where we don't make any swaps. Right, so here's the fourth pass. Right, we compare 1 and 2. Those are not out of order, so we don't swap them. We compare 2 and 3. Those are not out of order. And we're done with the fourth pass. Right? And since we haven't made any swaps during the fourth pass, we're done. Right? So now we know that the entire array is ordered. Okay? So that's bubble sort. Now, here's the implementation of bubble sort. But before we look at that, let's look at a visualization of that. So you can see some animation. So here is a nearly sorted array. I'm just using this to demonstrate that if we don't need to make any swaps, then we're done. So let's sort this array. Okay, so the green bars are showing which elements are being compared, right? And the sorting actually stops after the third pass because no swaps needed to be made, right? So here's the animation again. And so here's the third pass now, and no swaps are made, so we're done, okay? Okay, so that's bubble sort, and here's the implementation of bubble sort, right? So we again have our items array and our low and high. Yep, question?
So even after it's sorted, it still counts as having a fourth pass, right? We don't stop right after the fourth pass.
Yeah, so we need that fourth pass. This is because after the third pass, we don't know yet if the array is sorted yet. Once we perform a pass through the array where we don't need any swaps, then we know that the array is sorted. Yeah, so that one extra pass counts. Yeah. Okay, so here is the implementation. Right, so here, our outer for loop actually starts from index high and decrements until it reaches index low, right? And the reason is we use this index I to keep track of where we actually iterate up to during each pass, right? Because each subsequent pass, we don't need to iterate up to the end, right? We only need to iterate to the end of the part of the array which isn't sorted yet. Right, so the first pass we do iterate all the way to the end, but during the second pass we iterate up to index n-1. Then in the third pass we iterate up to index n-2 and so on. Okay, so that's the purpose of the outer loop. Now inside the loop, we have another loop which actually performs the pass through the array. And notice that we have a swapped variable to tell us whether we should swap an element or not, which tells us whether we've swapped two elements or not. Right, so during the pass, we compare adjacent elements, right? We compare items j and items j plus 1. And if items j is greater than items j plus 1, which means the item on the left is greater than the item on the right, that means they're out of order, so we swap them. Right? And at the end of the pass, if we haven't made any swaps, then we break out of the loop, and we're done. Okay, so that's the implementation. Now, how about the time complexity? Right, so here there is actually a difference between the best case, the worst case. So in the best case, the array is sorted, right? So that's the best case for bubble sort, and that's because only a single pass is required, right? We make one pass through the array, we don't make any swaps, and that means the array is sorted. Right, so in total, we make n-1 comparisons. Right, we also don't make any swaps, so the best case time complexity is just O(n). Okay? So that's the best case. What is the worst case? Well, the worst case is when the array is reverse sorted, right? And that's because we're going to need to make all the passes through the array, n-1 passes to be exact. Right. During the first pass, we make n-1 comparisons, right? Because we're comparing each pair of adjacent elements, right? There are n-1 such pairs. During the second pass through the array, we make n-2 comparisons, because we don't need to look at that last element anymore, and so on. And during the final pass, we make just one comparison. Right, and that means the total number of comparisons is this expression again, which you already saw during selection sort, right? And this is what it's equal to again. And every time we compare, in this case, where the array is reverse sorted, we need to perform a swap, right? So the number of swaps is also this expression here, half of n times n-1. Okay, so this means that the worst case time complexity is big O of n squared. Okay, so that's the worst case. Now, how about the average case? Now, the average case is actually a bit harder to analyze, right? But it turns out to be O(n) squared, and you can kind of figure this out mathematically. There is a kind of explanation in the appendix of these slides. I'm not going to show them because it's kind of tricky, but you can prove that for a randomly ordered array, bubble sort needs to perform this many swaps on average, right? And that happens to be big O of n squared. Okay. But what we can also do is we can generate random sequences of numbers and sort them and see how long the algorithm takes. Right. So here now I'm going to just go over to my terminal, and I'm going to use, so here I have a bunch of different programs for all the sorts, but I also have a program to generate random sequences. Right? So this gen program will generate a sequence of numbers in the order that I tell it. So I can generate numbers in ascending order, descending order, or random order. Right, so since I actually want the sorting algorithm to take a bit of time, let's generate 10,000 numbers randomly ordered. And now I'm going to pass that output to my bubble sort program. Right, so bubble sort. And we can see that it sorts the numbers correctly. Right, but now I want to time how long the program takes. Right, so to do that, I'm going to put the time command in front of bubble sort and run it. Right, so after all the outputs, it tells me how long the program took. Right, and in this output, it actually gives me two different times. Right, this one is called the user time, and this one is called the system time. So here we only care about the user time. So we can see that if we sort 10,000 numbers using bubble sort on this machine, it takes about 0.23 seconds. So 0.23 seconds. Now let's see how long it takes if I try to sort 20,000 numbers. Right, so remember with 10,000 numbers, it takes about 0.23 seconds. Right, so for 20,000 numbers, it takes about 0.89 seconds, and it's pretty consistent, right? 0.89 seconds or 0.9 seconds. So you can see that it's taking about 4 times as long, right? So if you double the input size and it takes 4 times as long, that's indicative of an O(n) squared algorithm, right? So yeah, you can see that bubble sort is O(n) squared on average. Okay. Okay, let's look at the properties of bubble sort. Okay, so bubble sort happens to be stable, right? And the reason it's stable is that first of all, we only compare adjacent pairs of items, right? And we only swap them if they're out of order, right? So there's no way for us to compare two items that are far apart from each other, which can end up, swapping one item over another item with the same value. Right? We only swap adjacent items. That means if there are two items with the same key, they'll eventually end up next to each other, right? But we'll never swap them over each other because they're not out of order. Okay, how about adaptability? So in our time complexity analysis earlier, we saw that if the array is sorted, right, the time complexity is big O of n. If the array is reverse sorted or sorted randomly, then bubble sort takes O(n) squared time, right? And this tells us that bubble sort is adaptive. Okay. Okay, and bubble sort is in place. Right, you can look at from the algorithm here that we only use integers and booleans, right? We don't have any temporary arrays or anything. So bubble sort is in place. Okay, so that's bubble sort, and now I think we'll take a short break, and a 5-minute break, and after this we'll continue looking at the other sorting algorithms. All right. Okay, let's get back into it. So now we are going to look at the remaining sorting algorithms in this part, which are insertion sort and shell sort. Okay, so let's look at insertion sort. Right, so how does insertion sort work? Right, so here's the method. So what it does is it first takes the first element and treats that as a sorted array of length 1. Right? And then it takes the next element, so the second element, and inserts that into the sorted part of the array so that the order is maintained. Right? And then after we do that, we're going to have a sorted subarray of size 2. Right? Then we take the next element and insert that into the sorted part of the array so that the array is still sorted. So now we have a sorted array of size 3, and so on. Right? So each time we insert an element, we increase the sorted part of the array by 1. Right? And if you remember the function that you had to do in the week 1 lab, I think it was insert ordered. Right? Insertion sort pretty much does that for every element in the array. Right? So here is an example. So we want to sort this array. So the first thing insertion sort does, remember, is it takes the first element and treats that as a sorted array of size 1. All right? And now, for each of the remaining elements in the array, it's going to insert the elements into the sorted part of the array so that the array remains ordered, or so that the sorted part of the array remains ordered. Right? So how does that work? Well, for the 1, right, to insert the 1, we're going to compare that with the element on its left, right, which is 4. And since 1 is less than 4, I need to insert the 1 to the left of the 4. Right? So what we do is we shift the 4 across. Right? So we shift the 4 to the right, and then we put the 1 at the start of the array. Okay? So the result is going to be this now. Now the next item is 7. Right now to insert the 7, we compare with the item on its left, which is 4. Right now, since 7 is greater than 4, I don't need to do anything. Right? The array will be sorted if I just leave the 7 where it is. Okay, so now we have 1, 4, 7 as the sorted part of our array. How do we insert 3? Well, again, we compare the 3 to the item on its left, which is 7. Right? 3 is less than 7, so I'm going to need to shift the 7 down to make room for 3. So we shift the 7 down. Now we compare 3 to the item on the left, which is 4. Right, since 3 is less than 4, we're going to shift the 4 down to make room for 3. And then now, since 3 is not less than 1, we're going to put the 3 down next to the 1. Right, so now we have 1, 3, 4, 7. Right, now, how do we insert 8? Well, we're going to, again, compare an 8 to the item on its left, which is 7. 8 is greater than 7, so we're going to leave the 8 where it is. How do we insert 6? Right, well, we compare 6 to the item on its left again. So 6, since 6 is less than 8, we're going to shift the 8 along. Then 6 is less than 7, so we shift the 7 along. And 6 is not less than 4, so we put the 6 down right next to the 4. Right, so now we have 1, 3, 4, 6, 7, 8. Okay, how do we insert the 5? Well, to insert the 5, we're going to need to shift the 8 down, the 7 down, and the 6 down, and then we're going to put the 5 right next to the 4. Okay. Finally, to insert the 2, we're going to need to shift down 8, 7, 6, 5, 4, 3, and then insert the 2 next to the 1. All right, and there is our final array. Okay, so again, let's show an animation of insertion sorts. Okay, so notice that kind of every item that we insert, we kind of hold it in a temporary variable, and then we shift the items along to make room for the elements. right? And now we're done. Okay, so that's how insertion sort works. Okay, now here's the code for insertion sort. And now this is a bit more complicated than the other ones, but here's how it works. So we first have an outer loop, right, which iterates starting from low plus 1. Right, so we start from index low plus 1 because remember at the start of the algorithm we take the first elements to be sorted. Right, so we kind of skip the first elements really, and then we iterate up to index high. Now for each element, we're going to store it in a temporary variable, right? So that way when we shift the elements to the left down, we don't accidentally lose the elements, lose the item. Right, so we store the item in a temporary variable. Then we're going to use another index variable to keep track of where we are up to when we are shifting items across. Right, so here in this inner loop, we're trying to pretty much find where the current item belongs, right? And we're shifting the items down on this line here, right? Items j equals items j minus 1, right? And we keep doing this while the item that we're trying to insert is less than the item on the left, right? So we keep doing this until that's no longer true, and then we insert the item at index j. Okay, so there's the code. Now, how about the time complexity, right? So first of all, the best case of insertion sort is when the array is sorted. Okay, when the array is sorted, every time we insert an element, right, we only need to perform one comparison with the item on its left, right? For example, when we're trying to insert the 2, right, we compare that to the item on its left, and since 2 is greater than 1, we just leave the 2 where it is. When we insert the 3, we compare that with the 2. Since 3 is greater, we leave that where it is. And we do that all the way down the array, right? So to insert each element, we only need one comparison, and that means we perform n-1 comparisons in total, okay? And that means the best case time complexity is big O of n, right? And also, we don't need to perform any swaps, right? Or any moves in this case. Right, how about the worst case? Well, the worst case is when the array is reverse sorted, kind of like bubble sort. Oops, sorry. So if the array is reverse sorted, then inserting every element is going to require more and more comparisons, right? When we, in this example, when we insert the 7, we compare that with the 8, right? And then we need to shift the 8 down and insert the 7. When we insert the 6, we're going to need to compare that with the 8 and with the 7. When we insert the 5, we're going to need to compare that with the 8, 7, and 6, right? So every time we insert a new element, we perform one more comparison than the element before, right? So inserting the element at index 1 is going to take one comparison. Inserting the element at index 2 is going to take 2 comparisons, and so on. Once again, we have this kind of arithmetic sum, right? One total number of comparisons is 1 plus 2 plus blah, 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 plus n-1, which is, again, big O of n squared. All right. So, and also here, in insertion sort, we don't really talk about swaps because we're not really swapping things. We are shifting elements down and then inserting the elements where it belongs, right? So here we usually talk about the number of moves or the number of shifts. Now the number of shifts is going to be the same as the total number of comparisons, right? Because every time we compare, we need to shift an element down. So the worst case time complexity is big O of n squared. Okay, now how about the average case time complexity? Well, the average case happens to be bigger than squared, and it's for the same reason as bubble sort, right? So I have this explanation of the average case for bubble sort. You can kind of apply this to insertion sort as well, right? But also just want to be clear that this kind of proof isn't accessible, right? So you don't need to worry about the proof if you don't want to, but you can have a look if you're curious. Okay, but you can also show that the average case is bigger than squared by generating random sequences and sorting them and timing them, right? And I already did that for bubble sort, so I'm not going to do it for insertion sort, but you'll get the same kind of result. Okay, how about the properties of insertion sort? So insertion sort is stable. We can see that because whenever we insert an element, right, we compare it to the element on its left, right, and we repeatedly shift elements down until the element on the left is less than or equal to the current element, right? And since we stop when there is an element that is equal or less, we're never going to swap an element over another element, which is equal to it. All right, so also insertion sort is adaptive, right? We saw that in our analysis. Right? Best case is ON when the array is sorted, and on average, it's ON squared. Okay, insertion sort is also in place, right? Just like selection sort and bubble sort. We can see from the code that we only use a constant number of variables and no temporary arrays. Okay, so that's insertion sort. Now, does anyone have any questions about insertion sorts? Nope. Cool. So yeah, that's insertion sort. Now, let's have a look at a more interesting algorithm called shell sort. Right now, the motivation for shell sort is based on the kind of limitations of bubble sort and insertion sort. Right now, these two sorting algorithms, they move elements by shifting them up or down one space at a time, right? If you think about bubble sort, we only compare adjacent elements and we swap them if they're out of order. Right? Insertion sort also only shifts elements up one at a time. Right? Now with shell sort, the question is, well, can we make the sorting algorithm more efficient if we compare elements that are far apart and then swap them, right? If we take elements that are far apart and swap them, then maybe we'll be able to move an item closer to where it belongs faster, right? So that's the idea behind shell sort. You know, if we make longer distance exchanges or swaps, can we be more efficient, right? And shell sort was invented by this guy, Don Shell. You know, the other sorts don't have names, aren't named after anyone because they're too simple. But yeah, shell sort. So with shell sort, there's an idea which is H sorting, right? So H sorting, and the idea is we say that an array is H sorted if we take every H element, and if we do that and the array is sorted, so let me rephrase that. So if we take all the elements that are, all the groups of elements that are multiples of H spaces apart from each other, and those elements are sorted, then the array is H sorted. And we'll see some examples of that, so don't worry. Let me actually skip to that slide. So here are some examples of H sorted arrays. Right? So the first array here is 3 sorted, right? Because if we take every third element, or if we take the groups of elements that are 3 or multiples of 3 apart from each other. So for example, the green elements here, 4, 5, 7, and 8, that's sorted. The orange elements 1, 3, 6, these are sorted, and the elements 0, 2, and 9, these are also sorted. Right, so that's an example of a 3-sorted array. Here's an example of a 2-sorted array. So this means all the elements that are multiples of 2 apart are sorted. Right, so for example, 1, 3, 4, 7, 9. Right, these are all in order, and the alternating indices 0, 2, 5, 6, and 8, these are also sorted. Right? And finally, we have 1 sorted, right? And that just means the entire array is sorted. Right? So the idea of shell sort is to H sort the array for large values of H first, right? And the idea is, again, to try to get the elements close to where they belong using large swaps. Right, so we H sort the array for large H, and then we progressively reduce the value of H, and finally we end with sorting with H equals 1. Right, so we 1 sort the array at the end. And that will guarantee that the array is sorted. Okay, so here is an example of shell sort. So suppose we start off with this array, and here we're going to start with H equals 3. All right, so in a real example, the array will be bigger and you'll use a different sequence of H values. But since I'm just showing an example here, we'll go with H equals 3. Okay, so when H equals 3, we want to make sure that all the groups of elements that are multiples of 3 spaces apart are sorted. Right, so there are 3 groups here. First we have, index 0, 3, and 6. So these elements are 4, 3, and 5. Then we have another group here, which is index 1, 4, and 7, which are 1, 8, and 2. Then we have another group, which is index 2 and 5. So these are 7 and 6. Right, so once we H sort the array with H equals 3, we get each of these groups in order. Right, so we have 3, 4, 5 here, 1, 2, 8, and 6 and 7. Right, and the way we actually H sort the array is by using insertion sort, but we compare each element to the element which is H indices away, right, instead of adjacent elements. So we would take this group of elements, 4, 3, 5, perform insertion sort on that group. Then we take 1, 4, and 7, perform insertion sort on that group. Then take the last group, index 2 and 5, and perform insertion sort on that group of elements. Okay, so after we H sort with H equals 3, this is what we get. Right, so notice that the array isn't quite sorted, but each element is now a little bit closer to where it belongs, right? Or most of the elements are. All right, so now let's try 2-sorting the array. Right, so when we 2-sort the array, we look at the groups of elements which are 2 spaces apart from each other. So we have 2 groups here, one which is 2, 3, 5, and 6. One which is 3, 6, 2, and 5. And after we 2-sort that group, we get 2, 3, 5, and 6. The other group is 1, 4, 7, and 8, right? And that group happens to be sorted already, so it just gets, it just ends up being the same after the 2-sorting, right? And here's the result of 2-sorting, right? So now we have 2, 1, 3, 4, 5, 7, 6, 8. Right, so now the elements are getting really close to where they belong. So as a final step, we do a 1-sort on the array, right? And this is pretty much just an insertion sort, right? So we perform an insertion sort through the array, and this is what we get. right? So we get a sorted array at the end. Okay, so let's see if this website has a shell sort. No, it doesn't. I suspect it doesn't because you have to kind of specify the H values, and there are lots of different H sequences. If you look at the Wikipedia page for shell sort, lots of people have tried different sequences of H values. But here is the implementation of shell sort. So this might look a little scary, but let's see, let's walk through it. So in the first part of the function, we're basically trying to find an appropriate value of H to start with, right? Because if your array is large and it has like 1 million items, then you want to start with a large value of H. Okay. Now, in the main part of the function, we see that there are 3 nested loops, right? Now, you might look at this and think, okay, the algorithm must be O(n) cubed, but it's not. That's because if you look at the outer loop here, right, it starts with the value of H that it found in the first part, and it repeatedly divides by 3, right? So, you know, we're not looping from 0 to n or anything. We're just taking the H value and then repeatedly dividing it by 3 so that it gets smaller and smaller. And inside the outer loop, we basically perform an insertion sort, right? Except instead of comparing each element to the item on its left, like comparing index j with index j minus 1, we are comparing each item with index j minus h, right? So we insert each item, but within that group of elements, which are H spaces apart. Okay, so that's the implementation. Now, the analysis of shell sort is a little tricky because the efficiency kind of depends on the H sequence. Right. Now, as I said before, lots of different people have tried different sequences of H values, but most of them have been found to be big O of n to the power of 3 on 2. Right? So this is slightly better than big O of n squared, and yeah, big O of n to the power of 3 on 2. So here's an example of a sequence which would give you this time complexity. And some other H sequences have been found to be a bit faster. So this sequence has been found to be big O of n to the 4 and 3. Right, but there is no real analysis. So there's no analysis where you can give it a random sequence of H values and it'll tell you what time complexity it is. You kind of have to figure it out empirically. All right, so that's shell sort. And the properties of shell sort are, first of all, that it's unstable. Right, it's unstable because you need to perform long-range swaps. And this can cause the same problem as what I talked about in selection sort. Shell sort is also adaptive. Right? The reason it's adaptive is because it pretty much uses insertion sort, right? A generalization of insertion sort where you compare each element to the elements H spaces away from you. Right? And because insertion sort is adaptive, shell sort is also adaptive. And shell sort is also in place, right? And in place because if you look at the algorithm, it doesn't use any temporary arrays. Okay, so that's shell sort, and here is the summary of the sorting algorithms that we've covered so far. Right, notice that in the worst case, right, these algorithms are O(n) squared, right? And in the worst case, shell sort is also going to be n to the power of something which is greater than 1. right? But the time complexity of shell sort depends on the sequence, which is why I've written depends here. Right, and here is the stability and adaptability for each of the algorithms. Right, now there's a brief aside here for sorting linked lists. Right, we're not going to be focusing on this, but for the first few algorithms that we talked about, selection sort, bubble sort, and insertion sort, you can kind of implement something which contains the essence of the sorting algorithm. So for example, for selection sort, one way you could sort a linked list, similar to the way selection sort sorts an array, is you go through the list, find the largest value, and then insert it. So first of all, you create an empty linked list, right? You go through the original list, find the largest value, insert it at the start of S, right, of your new list. Right, then you find the second largest element, then you insert that at the start of S, then you find the third largest element, insert that at the start of S, and so on. If you keep doing that, you'll end up with a sorted list. Okay, and you can do something similar for bubble sort and insertion sort. So we're not going to go through this in detail, but for shell sort, that's kind of hard to implement for linked lists, right? Because in shell sort, you kind of have to compare an element with an element which is h spaces away, right? So how do you do that with a linked list? You can't really do that, right? Because with a linked list, you don't have random access into the array, right? You can't specify an index and go to that index straight away. You have to actually iterate through the linked list until you find the appropriate index. Okay. So, yeah, shell sort is a no-go for linked lists. Okay, and that is the elementary sorts. So, yeah, there's of course the appendix where I go through the average case of bubble sort, but that is it. So now we'll start looking through the next part of sorting algorithms, which is divide and conquer sorting algorithms. And we won't be able to finish this today, but we'll continue on Thursday. Okay, so divide and conquer sorting algorithms, right? Divide and conquer is a cool term. What does it mean, right? So what is the divide and conquer algorithm? So it's an algorithm that splits a problem into two or more subproblems, right? Then it solves those problems recursively and combines the results. Right, so you see why we needed to learn about recursion. This is one of the reasons. Right, so remember what recursion is. Recursion is solving a problem via solving smaller versions of the same problem. Right, so divide and conquer kind of sounds like that, right? Where we split a problem into two or more subproblems. But the difference is how many subproblems we split it into, right? With recursion, with divide and conquer, you have to split it into two or more subproblems. Right, and if we use this method or this kind of algorithm, we can achieve better time complexities than big O of n squared. Right, in fact, we can go, we can get to as good as big O of n log n. Okay. So let's talk about the first divide and conquer algorithm, which is merge sort. Right, now, merge sort was invented by this guy, John von Neumann, in 1945. And how does merge sort work? Right, so what it does is it splits the array. So suppose you have an array that needs to be sorted, where you split the array into two roughly equal-sized parts. Right, so for example, in this diagram, we show the array being split into the left half and the right half. Then what do? we recursively sort each of the partitions, right, each of the halves, right? So notice here we are applying merge sort recursively on the left half, and we are also applying it recursively on the right half, right? And after we've done that, we now have two sorted subarrays, right? Both halves of the array are sorted, and all we have to do is to merge them into a sorted array, right? So we take the two sorted parts and merge them. And so the question is really, how do you actually merge the two sorted subarrays, right? That's something that we'll look at in just a bit. Right, but first of all, here's a nice diagram of merge sort to really show you what's happening, right? So if we have an array containing 8 elements, then we split that array into two subarrays containing 4 elements. Right now, each of those gets split into two small subarrays containing 2 elements. Each of those gets split into two subarrays containing just 1 element, right? And once you have subarrays containing 1 element, right, that's when you begin the merging process, right? So, for example, the 5 and 2 get merged into a sorted subarray containing 2 and then 5, right? The 4 and 7 get merged into 4, 7. The 1 and 3 get merged into 1, 3. The 2 and 6 get merged into 6. Then these two, then now we have two sorted subarrays of size 2. So we merge that into a sorted subarray of size 4. And we do the same thing on the right. So we get 1, 2, 3, 6. Then finally, we merge the two arrays of size 4 into an array of size 8. Okay? So that is how merge sort works. Okay, so now let's go into a bit more detail about the splitting and merging. Right, so how do we actually split the array? Well, when I say splitting, I don't mean we physically split the array into two parts or that we create two new arrays. So we don't actually do any of that. What we actually do is we just calculate the midpoints of the array, right? And then we recursively call the function on each of the halves by passing in the appropriate indexes, right? So we calculate the midpoint, right? That's low plus high divided by 2. And then to recursively merge sort the left half of the array, we call the function, right? We call the sort function, and we pass it index low and index mid, right? This corresponds to the first half of the array. Then we recursively call the function on mid plus 1 and high, right? That will recursively sort the right half of the array. And that's how we split the array, right? All we're doing is calculating the midpoints and then recursively calling the function, and that's it. Right, so there is no actual cost or no huge cost to splitting the array. The time complexity is just 0.1 for splitting, okay? Now, that's splitting, but the more complicated part is merging, right? Merging is where most of the work actually gets done during merge sort, right? Because splitting is really easy. What happens once we get down to those individual elements and we have to merge them, right? So here are the details of merging, but the main points is that it uses a temporary array, right? So if we have two sorted subarrays, what we'll do is create a temporary array, and then we'll merge the items from those arrays into the temporary array, and at the end we copy it back into the original array. Right, now I'm not going to read these points here, but I'll just show you guys the visuals. Right, so suppose we have two sorted subarrays here, where we have 2, 4, 5, 7. So that's one sorted subarray. Then we have 1, 2, 3, 6. That's another sorted subarray. The reason I'm putting them right next to each other is because that's what the array actually looks like during merge sort. Right, it's just an array where all the elements are contiguous. Right, and during the merging step, what we do is we have two indexes, one to each half of the array that keeps track of the smallest elements that we haven't merged yet. Right, so at the beginning, these are just going to point to the smallest or the first element in each half. And we also have our temporary array, and we're going to have another index or pointer to that to keep track of where the next item is going to go. All right. So what are we going to do? Well, since we know that each of the subarrays, each of the halves are sorted, right? The smallest elements must be the first elements of one of the halves, right? Must be one of those elements, either this element or this element. Right, so what do? We compare the elements, right, and we take the smaller one and copy it into the temporary array, right? So nice and simple. And we also move this pointer along, right? So now we have two elements which are the same, right? We have a 2, which we haven't used yet on the left half, and we have this 2 on the right half, right? So what do? If we have items that are equal, then we take the item from the left half, okay? And this guarantees stability, right? This makes sure that merge sort is going to be stable. So we take from the left half and copy it down. Then we're going to repeat. So now we're comparing 4 and 2, right? Since 2 is smaller, we're going to copy that down. Now we compare 4 and 3. Since 3 is smaller, we copy that down. Now we compare 4 and 6, right? Since the 4 is smaller, we copy that down. Now we compare 5 and 6. Since 5 is smaller, we copy that down. And now we compare 7 and 6, and we copy the 6 down. Right? And after we're finished with one half of the array, right, see that we've used up all the elements in the right half. But once that happens, we can now take all the elements, all the remaining elements from the other half and just copy them down. Right? So we copy the 7 down here, and we're done. Right? Of course, you have to copy everything back to the original array, but then you're done. Okay, so there's the first example. Now here is another example, just to show you that the merging process also works if you have small arrays. Right, this sort of happens at the lowest levels of merge sort, right over here. Right, so if you have two subarrays of size 1 and you want to merge them, the process is exactly the same. Right, so you compare 5 and 2. Since 2 is smaller, you copy that down. Now we've used up all the elements from the right half of the array, so we copy everything from the left half down. Okay. So that's how the merging process works. Right, now to analyze merge sort, well, not merge sort, but the merging process, if we have two sorted subarrays and the total number of elements is n, what is going to be the time complexity? So it turns out the time complexity is going to be big O of n, right? Where n is the total number of elements in both subarrays. Okay, and the reason for that is we essentially, in the worst case, end up performing n comparisons, right, between elements. Right? So every time we compare two elements, we copy an element down into the temporary array. Right? So it stands to reason that the number of comparisons we make is going to be at most n. Right? So comparison, 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 comparison. Okay, so n comparisons at most. Okay, so what that means is that if we have two subarrays of size 1 and we merge those into a subarray of size 2, then that takes about 2 steps, right? Or 2 comparisons, right? If we have two subarrays of size 2 and we want to merge those into a subarray of size 4, then that's going to take about 4 steps, right? Or 4 comparisons. if we merge two subarrays of size 4 into a subarray of size 8, then that's going to take about 8 comparisons. Right. So yeah, so that's the analysis of merging, and that's going to factor into the analysis of merge sort as a whole. But before that, here's the implementation of merge sort. Right, so you can see that the merge sort function itself is really simple. Right. Of course, since merge sort is recursive, we have a base case. Right, the base case is if there is only one element in our subarray, or no elements, then we just return, because an array of size 1 is sorted by default. Right. Then, if our array is bigger, then we calculate the midpoints. Right. Then we recursively merge sort the left-hand side of the array, right, from index low to mid. Then we recursively merge sort the right side of the array from mid plus 1 to high. Then we perform the merge, right? So we merge the two halves of the array together. And here we pass it index low, index mid, and index high, so that the merge function knows where the middle point is. Okay, and here is the merge function, right? So here is where the bulk of the work is done. Right, so let's see what happens here, right? So in this function, we first create a temporary array. Remember I said that when we merge, we need a temporary array. So we malloc that. And then we create the 3 indexes, right? Remember, these are the arrows that I showed in the example. So index I, index j, index k, okay? And then in this while loop here, we compare elements at index I and index j, right? If index I is less than or equal to index j, then we copy the left index, index I, into the temporary array. Otherwise, we copy index j into the temporary array, right? And then we keep doing that while we haven't used up all the elements from any half. But after we've used up all the elements from one of the halves of the array, then this while loop is finished. And the point of these 2 while loops is to copy the items from the unfinished parts of the array. Right? So if the left half is done, then we copy the remaining elements from the right half. If the right half is done, then we copy all the elements from the left half. Okay? And here, in this loop, we just copy all the elements from the temporary array back to the main array. Okay, so that's the implementation. Right, and how about the time complexity? Right, well, with analysis, it's nice to kind of bring back this diagram because it kind of shows you, the different levels of recursion here. But here is the analysis, right? There are kind of 2 things to analyze. First, there's the splitting of the array, and there's the merging, right? Now, with splitting, remember that we don't split the array physically, right? In order to split, we're simply calculating the midpoint and calling the function on both halves, right? So splitting once takes O1 time, right? How many times do you actually have to split the array? You have to split it n-1 times, right? If you count here, the number of splits that have to be made, that's 1, 2, 3, 4, 5, 6, 7, right? 7 splits for an array of size 8. Okay, so the splitting part is going to be ON, right? Because each split is just O1. But how about the merging, right? So this is where the analysis from before comes in. Remember that when we merge 2 subarrays of size 1, right, that's about 2 steps or 2 comparisons, and so on, right? So when we do the analysis, we kind of have to consider how many levels of merging we need to perform, right? How many levels of recursion there are in total. And also we have to figure out how many comparisons we perform across each level, right? If we start with an array of size n, right, then there are going to be about log n levels of recursion, right? Log n rows here, right, of recursion, right? Now, if you look at this level where we have arrays of size 1, right, if I want to merge these two elements into a subarray of size 2, then that's going to take 2 comparisons. Right? If I want to merge these two, that's going to take 2 comparisons. If I want to merge these two, that's going to take 2 comparisons. And if I want to merge these two, then that also takes 2 comparisons, right? So in total, across the entire level, the number of comparisons made is going to be 8, right? Or n, the number of elements in the array, right? In the original array. Right. Now let's look at the next level, right? If I have 2 arrays of size 2 and I want to merge it into an array of size 4, right? That's going to take about 4 comparisons. And let's look on the other side. If I want to merge these 2 subarrays, that's also going to take 4 comparisons, right? So across this level again, the merging is going to take about n comparisons, right? Or n steps, right? And same thing for the final level, where we have to merge the 2 halves into one array. All right, so what we end up with is we have to merge n numbers exactly log base 2n times, right? So that means the time complexity for the merging is going to be big O of n log n, right? And since big O of n log n is bigger than big O of n, the time complexity of merge sort is big O of n log n. Okay, so that's the analysis. Now, since we have run out of time today, we will continue with merge sorts on Thursday, and we'll also go on and talk about quick sort and other sorting algorithms. Right, so see you on Thursday.